Okay, in this fourth video, we're looking at the idea of the Boltzmann constant. Now, in the third video, we looked at the ideal gas equation, which tells us the relationship between pressure, volume, and temperature for gas. And we find that basically for the constant proportionality, when we're dealing with these things in terms of moles, is R, the molar gas constant. Now, what happens if we don't want to deal with it in terms of moles, but we want to deal with it in terms of number of particles, okay, or number of molecules? Well, there's an easy blag, and the Boltzmann constant allows us to do that. The Boltzmann constant is simply the molar gas constant divided by Avogadro's number, the number of particles that are in 1 mole of a substance. Okay, rearranging this simple idea over here to put the molar gas constant in terms of the Boltzmann constant and Avogadro's number, we can then substitute this in for the R in the ideal gas equation. That gives us pressure times volume equals N stays the same, and we got the Avogadro's number times by the Boltzmann constant times by T. Now, you're probably at this stage aware of the fact that if you have the number of moles times by the Avogadro's number, and the Avogadro's number is the number of particles in 1 mole, and these two things together will give you the number of molecules. And so it's just another version, okay, we get another version of the ideal gas equation, but we get it this time in terms of the number of molecules and the new constant of proportionality, which is the Boltzmann constant. Now, the Boltzmann constant is basically the Avogadro's number divided by, the molar gas constant divided by Avogadro's number, and it's 1.38 times 10 to the minus 23 joules per Kelvin. And so that is the Boltzmann constant. It's just a different constant of proportionality that we deal with when we are looking at number of molecules as opposed to number of moles in an ideal gas equation. And that's the relationship there.